Today we are going to focus on final repository research. What are we going to talk about? A brief recap how we handle fuel in Germany, then some information about the chemistry of the long-lived fission product Technetium, and then we'll look at the geochemistry of Technetium. That means we will be conducting sorption studies with the mineral pyrite, and by the end of the video we will know one more way in which the fission product Technetium interacts with minerals. Why is all of that relevant? In Germany we have been using nuclear fission indirectly to produce electricity for several decades. Many different processes take place in the nuclear fuel of these nuclear power plants. Nuclear fission and transmutation. In other words, the production of small fission products and elements heavier than uranium, so-called transuranic elements. Plutonium or americium, just to name a few. All these elements, both the fission products and the transuranic elements, are contained in a German fuel element after 5 years of successful operation. Germany does not recycle its own nuclear fuel, which means that the nuclear fuel is simply just stored as it is, more or less. But there are countries that recycle it, and in the process dissolve it, change its composition again, but we in Germany don't do that. What you have just seen were images from Sellafield. It used to be a reprocessing plant. The largest in Europe is now Le Hague in France. However, freshly spent nuclear fuel is simply too hot. Not only in terms of radioactivity, but literally. The decay heat of short-lived fission products produced is so high that the rods must be first placed in a cooling pond. After a cooling off period of about 5 years, many highly active fission products have now decayed. 5 years is a reasonable time period in which very heat-producing, i.e. short-lived radionuclides can be completely decayed while using some active cooling. The heat produced afterwards can then just be dissipated by passive cooling systems. Some other nuclides, long-lived fission products, and a large proportion of the transuranic elements are still contained inside of the fuel element. The entirety must now be placed underground. All in all, a deep geological repository is proven to be the safest method of dealing with highly radioactive waste in the long term. Above ground storage would be far too easy as a target, especially from a geopolitical point of view. Since deep geological repositories are the safest way to store radioactive waste, the retention of said radionuclides in minerals plays a decisive role in the corresponding safety assessment. And we will take a closer look at this today. If we were to play through the worst case scenario, it would involve the release of radioactive substances, i.e. if the packaging material, the so-called cask, were to fail for whatever reason. In Finland, the first deep geological repository is being set up with a so-called multi-barrier system. For the radionuclides to be considered released, they would first have to come out of the uranium dioxide fuel itself through the cladding, i.e. the casing of the individual uranium dioxide fuel pellets, then through the cast iron in which the fuel rods are contained, and then, in the case of Nordic countries, through another copper cladding again. The chances that the radionuclides will actually get into the environment naturally decreases with each additional barrier. In what I have described so far was the first technical barrier. But even after crossing the first technical barrier, the radionuclides are still not considered to be released into the environment. Because they are simply not. They are still inside the multi-barrier system. Behind the technical barrier, there is still the mineral barrier. In this case, it is made of bentonite clay. And only then do the radionuclides encounter the host rock. If the radionuclides reach the host rock, they are considered to have been released into the environment. And even this host rock must also have a very high thickness. Now, of course, it would be A, good if something like this does not happen, and B, if it did, then the radioactive substances or the radionuclides would not spread through the entire soil and contaminate the groundwater, for example. This immobilization, i.e. the stopping of the spread of radionuclides, can be achieved both by microorganisms and the rock itself, for example. In this video, we'll focus on the immobilization of the most troublesome fission product, Technetium. Why is Technetium so troublesome in this context? It is one of the longest lived fission products and it has a half-life of 211,000 years. And is produced in very high quantities by the fission of uranium-235 and plutonium-239, which are our best known nuclear materials. So we have a lot of it, it stays around for a very long time, and now there's something else. In one chemical form, it is not only chemically stable, but it's also extremely mobile. So it kind of has all the properties that we don't want radioactive substances to have if they are meant to be retained in the castor containers. Now let's talk chemistry. The chemical form I just mentioned is the pertechnetate ion, TCO4 1-. In this form, technetium has released all of its valence electrons and is therefore present in the oxidation state of +7. Another oxidation state, which is also quite stable, is the +4 oxidation state. Under environmental conditions, we then have mostly some technetium dioxide hydrate. In contrast to the pertechnetate, this form is poorly soluble in water and significantly less mobile. The reduced mobility can be explained by the fact that technetium 4+ interacts well with surfaces. It would be very handy if we could convert the pertechnetate into this technetium dioxide hydrate. However, that does not just simply happen. It does not have to be technetium dioxide. A reduction to the +4 oxidation state alone should be sufficient to significantly reduce the mobility of the technetium. For example, this could be achieved with redox active iron 2 minerals. Among others, the TechRad research team, led by Dr. Mayordomo, is now working on this exact task. This work is being carried out inside of the glove box. This prevents reactive atmospheric oxygen from disrupting the reaction and causing unwanted side reactions. Some equipment has to be brought inside. The glove box is then filled with chemically inert nitrogen gas. The mineral that is to be examined today for its immobilizing properties for technetium is pyrite. Chemically speaking, pyrite is iron disulfide, containing iron in the oxidation state of +2, which is exactly what is very important for us today. Pyrite is also known as fool's gold and is usually known as this beautiful glittering mineral, but since we are in nuclear chemistry, we are using 36.8 milligrams of just iron disulfide as a powder. We need this idolized pyrite to carry out some basic investigations and to rule out some more variables. In the meantime, the equipment has also been flushed with nitrogen and can now be placed inside of the glove box. Speaking of variables, the pH value is also a variable in the environment. In this case, we first want to collect data for just one pH value. To do this, the pH measuring probe is calibrated again. This is done with various buffer solutions of a well-known pH value. The pyrite is placed in deionized water and shaken well. This affects the pH value, and accordingly the pH value must be corrected to the desired level. For longer experiments, the entire system must be shaken, and as a extra protection, bags are placed around the Falcon tubes again because technetium contamination is really annoying. This is the potassium pertechnetate stock solution with a concentration of 0.1 millimolar. If this is added, the whole mixture must now also be labeled as such afterwards. In order to determine the remaining technetium concentration after sorption by means of liquid scintillation measurements, based on a known technetium concentration, a sample of the suspension is taken. The suspension can now be separated in a centrifuge tube. We hope that the supernatant is inactive, as this would mean that all of the mineral sediment has sorbed all of the activity. Half a milliliter was taken out of the supernatant and placed inside of an LSC vial. However, before it can be placed in the measuring device, a wipe test must be carried out to ensure that there is no contamination on the outside. A nice little note is attached, and depending on the degree of contamination, you will receive a certificate with one of the 3 marker colors. This vial was not contaminated, so onto the scintillation detector we go. Roughly speaking, liquid scintillation measurement works as follows. A sample decays radioactively. Radiation particles, such as beta or alpha particles, can excite chemicals inside of the scintillation cocktail. This excitation is emitted in the form of light, and the device can then measure this glow of the sample to draw conclusions about how much activity was inside of the vial. If you want to know more about this, I will link a video here. It's a bit pointless to now show just a spectrum with hardly any technetium activity, but this is what we wanted to have. This experiment is based on a paper written at the HZDR. It was shown that at a measured pH value of about 5.5, 97 to 100% of the dissolved pertechnetate could be immobilized. Sure, I can easily write down the reaction equation like this. What does the structure look like now after sorption? To investigate this, SEM, scanning electron microscopy, Raman spectroscopy, and XAS, X-ray absorption spectroscopy were used. Now let's take a look at the SEM image. You can clearly see that the surface has changed. There are two ways in which the technetium is structurally immobilized by the pyrite. So now let's take a look at this iron 3+. This is present in mineral form as an oxide. When the sorption experiments are carried out at the pH value of below 7.5, hematite is formed, and above a pH value of 7.5, magnetite forms as an iron 3+ containing mineral on the surface of the pyrite, which has interacted redox actively with the pertechnetate ion. So the formation of the secondary iron mineral on top of the pyrite and the immobilization of the technetium are mutually dependent on each other. So only because the redox reaction takes place between the iron 2 of the pyrite and the technetium of the pertechnetate, we now have the iron 3+ forming these secondary iron minerals and the immobilization of technetium. Let's take a closer look at this mineral. Hematite is completely oxidized iron oxide. Its composition is Fe2O3. If we look at the structure, we can see orange iron 3+ ions surrounded by red marked oxygen ions. This geometry is described as a slightly distorted octahedron. Magnetite is a mixed valent compound with the composition Fe3O4. This means that we both have 2 iron with the oxidation state of +3 and 1 iron ion with the oxidation state of +2 present. This can also be seen in this diagram. Octahedrically surrounded iron 3+ ions and tetrahedrically surrounded iron 2 ions. Now back to the immobilization. The weakest type of immobilization is surface sorption. But even here, there are different degrees of interaction. In the simplest form, we have a hydrated radionuclides that can be held electrostatically together with its hydrate shell onto the surface. This so-called outer sphere sorption is based on van der Waals forces and therefore is not particularly strong. If at least one part of the hydrate shell is removed, a chemical bond may form between the components of the mineral and the radionuclides itself. This is then referred as an inner sphere complex. This could also be measured here. In this case, sorption of technetium dimers by oxide parts of the iron oxide was demonstrated. In other words, there is a Tc2O8 unit that shares 2 oxygen atoms with the iron oxide. This is essentially an edge bond with the hematite. That was demonstrated using XFs, and this type of immobilization is very strong. Further interaction via OH groups are of course always possible. This means that the surface change we saw through the electron microscope was in this case due to the formation of secondary iron minerals on the surface of the pyrite. And these secondary minerals such as hematite have technetium dimers stick to them. And then there is the strongest type of immobilization, namely incorporation into the mineral. Technetium 4+ can replace iron 3+ in the crystal lattice as both have the identical crystal radius. This means that during the redox process, the iron ions can actually dissolve out of the crystal. Technetium can be cooperated into the structure of the existing iron oxide, and then the mineral can continue to grow as magnetite behind it. This iron oxide layer is not passivated. The technetium is practically buried in the mineral. This also means that if oxidative processes in the environment oxidize the immobilized technetium 4+ to pertechnetate again, which should then be released, this dynamic surface, which is not passivated, provides a constant reservoir of iron 2+ that can reduce the technetium back again, allowing this to be present as technetium 4+ and be cooperated even more stably into the newly formed magnetite phase. A lot of cool stuff. Technetium sulfur compounds can occur in a sulfur containing environment such as this one, but this could not be detected in this experiment. A partial release of technetium was observed over a longer period of time. Long means in this case 2 months. So longer studies are still needed, but it's already very impressive how well pyrite can immobilize technetium over such a wide pH range. So we learned quite a bit in this video. First of all, minerals can be involved in the immobilization of radionuclides in the environment. And we also learned what immobilization looks like structurally. and at a very advanced level that iron 2+ containing minerals are extremely good at immobilizing technetium as redox active minerals. There are many other studies and investigation methods for the immobilization of radionuclides by minerals, and I will show you one of these in an upcoming video about surface infrared spectroscopy. With that, a big thank you goes out to Tsiong, Sebastian and Vijay from the TechRad group who did all the chemistry work today, and to Dr. Natalia Mayordomo, head of the TechRad Junior Research Group at the Institute for Resource Ecology at the Helmholtz-Zentrum Dresden-Rossendorf. And of course, thank you to you, my patrons, for the financial support. With that being said, thank you for your attention and goodbye.